Okay, so the next module, we're going to focus on the other type of chemical bonding that you come across. And as we mentioned at the beginning of the ionic bonding module, the other type of chemical bonding that you come across is what is known as covalent bonding. And to sort of get into more of an introduction about this type of bonding, we're going to take a look at covalent molecules, and we're going to take a look at covalent compounds. So covalent compounds are made up of molecules of that compound. So for example, if you have something, if you have water, H2O is an example of a covalent compound. If you have a sample of water with you, that sample of water is going to be made up of millions and millions of molecules of water. So basically anything covalent, a covalent compound, is made up of millions and millions of molecules of that compound. In a similar sense, we sort of talked about how elements are made up of atoms of that element. And then in terms of ionic compounds, they would be made up of formula units of that compound. So covalent compounds are made up of molecules of that compound. Now, in addition, some elements exist in a diatomic form in nature. And essentially, when elements exist as a diatomic form in nature, you have two atoms of that element that are covalently bonded together. So in nature, those elements actually exist as molecules, examples of which are hydrogen, H2, which we'll discuss very shortly in more detail, oxygen, O2, nitrogen, N2, and the halogens, fluorine, chlorine, bromine, and iodine. They exist in a diatomic form in nature as well. So covalent compounds are made up of covalent bonds. And we know that covalent bonds result when atoms share electrons, specifically when nonmetal atoms share electrons. And again, this is based on the underlying rule of chemical bonding, which of course is the octet rule, that the reason why chemical bonding takes place to begin with is that atoms want to share electrons or participate in chemical bonding in order to satisfy the octet rule. Now, in terms of covalent bonds, you essentially have them between nonmetal atoms that come from groups 4A, 5A, 6A, and 7A in the periodic table. Now, on occasion, the elements in group 8A could participate in covalent bonding as well. But really the most important thing is the fact that essentially this involves non-metal atoms, okay? That's really the key part, is that when you have covalent bonds, covalent bonds formed between non-metal atoms. All right, so let's start really at the beginning. And the simplest, basically, element that exists in nature as diatomic, or exists, as a diatomic molecule in nature, is hydrogen. So based on the octet rule, each hydrogen wants 2 electrons, okay? Basically 2 valence electrons, or 2 electrons total in this case. Now, essentially, one way we can show this is with what is known as a Lewis dot or an electron dot structure. With a Lewis dot or an electron dot structure, we use the chemical symbol for elements, or chemical symbols for elements, and we use dots for valence electrons. Okay, so if we were going to apply this to hydrogens to form H2, each hydrogen has 1 electron total, which would be its 1 valence electron. And the goal for the 2 hydrogens is to get to 2. Now, one of the things to keep in mind, and that's what's in blue over here, is that shared electrons count for both atoms that are sharing them. So instead of one gaining 1, which means the other one has to lose and basically go down to 0. In other words, if there was electron transfer taking place, one would gain the 1 electron, which would be happy, because it would go from 1 to 2, but the other would lose and it would go from 1 to 0. So instead of gaining or losing taking place transfer, instead what they do is they decide to share. they're one valence electron between each other. And the way we can draw that in an electron dot or a Lewis dot structure is to draw a dash between them. Okay. And that dash between the two hydrogens in H2 represents what is known as a single bond. So an electron dot or Lewis dot structure, when you see a dash between two atoms, a single dash, a single line, maybe not a dash, but really a single line between two atoms, that is used to represent a single bond. And a single bond, in a single bond, you have a shared pair of electrons. So in other words, you have two electrons being shared. Okay. And as we'll see a little bit further on in the module, more than two electrons can be shared between atoms. But between hydrogen and H2, you have a single bond, so two electrons are being shared. So now, how many electrons does each hydrogen have? This one on the left has two, because that line represents two electrons being shared, and shared electrons count for both atoms that are sharing them. So this hydrogen atom has two electrons. This hydrogen atom has two electrons. Now the octet rule essentially is satisfied, and both hydrogens are happy. Okay. So here's a little bit more of a description of it. You know, you have two hydrogen atoms that are far apart, no attractions that are present. What attractions would you have? Well, the nucleus, which has a positive charge, would be attracted to the electron on the other atom. The nucleus of one atom would be attracted to the electron of another atom. So you have that sort of going in two directions, which is going to pull those atoms closer. And eventually they're going to be close enough, but they say, you know what, let me go from being less stable and having one valence electron or one electron total to now being more stable and having two valence electrons or two electrons total. And that's really what you see on the bottom here, where we're not going to sort of get into this idea of orbital overlap or anything, but the electrons are being shared in sort of this area where the atoms are sort of close enough to each other. In this picture here, that sort of represents the single bond. Now, they don't want to get too close to each other, because then you have the nuclei being too close, and there you sort of lose the force of attraction. Now you have sort of repulsive force. So we're not going to get into all that detail, but they start far apart, they inch closer to each other, and when they're close enough, they say, you know what, let's become more stable, and let's share those two electrons between each other. Okay. So let's take a look at another example. Let's take a look at fluorine. So fluorine is another example of something, of an element that in nature exists as something diatomic. So essentially in a fluorine F2 molecule, each fluorine atom shares one electron to attain an octet. So let's go into that in a little bit more detail. So fluorine, based on the periodic table, is in group 7A. And we know that if you're in group 7A or 17, how many valence electrons do you have? You have 7 valence electrons total. So there's our two fluorine atoms with 7 valence electrons. So again, the goal for each fluorine is to get to 8. Okay. So the goal is 8 valence electrons. All right. Just like for the majority of the elements in the periodic table. Just like for both fluorines, they each have 7. The goal is to get to 8 valence electrons. So again, instead of one gaining and one losing, what the fluorines decide to do is essentially they decide to share one valence electron between them. And when you do, you end up with something that looks like the following. Now, let me get into a little bit more detail about this. So the fluorines are connected together by a single bond. But each fluorine still has electrons that are a part of it that are not involved in any bonding. And these electrons have a term associated with them. Okay. These electrons are what are known as lone pairs of electrons. So you have that here, you have that here, you have that there, you have that in these other places as well. What essentially defines lone pairs of electrons? Well, lone pairs of electrons are not involved in chemical bonding. And for fluorine, none of the other electrons really want to participate in chemical bond formation, because if they share one each, they go from 7 valence electrons to 8. Now, one thing to keep in mind, and that's on the bottom here, is the fact that lone pairs of electrons only count for the atom that they are on. So if we go back now and take a look at each fluorine after the 1 electron is shared between them, this fluorine atom has 2, 4, 6, 8 valence electrons. This fluorine atom has 2, 4, 6, 8 valence electrons. So the octet rule for both is satisfied. Okay, so far in our electron dot or Lewis dot structures, not only can you have single bonds in the covalent bonding world to satisfy the octet rule, but then there are also lone pairs on atoms themselves that don't participate in chemical bonding, and they only count for the atom that they are on. Okay, so now let's take it a step further. And now let's take a look at a couple of examples of covalent compounds, which would be made up of molecules of that compound. On this slide, the example we're going to take a look at is a compound known as methane Ch4. It's actually the simplest organic compound that exists. And what we want to talk about here is how the carbon and the 4 hydrogens come together to form methane. So carbon has 4 valence electrons. The goal is to get to 8. Again, how would I know the 4 valence electrons? Carbon is in group 14 or 4A in the periodic table. And if you're in group 4A or 14 in the periodic table, you have 4 valence electrons. And just like most of the other elements in the periodic table, the goal for carbon is to get to 8. We know that each hydrogen has 1 valence electron. Essentially, it has 1 electron total, and therefore it has 1 valence electron. The goal, of course, for hydrogen can't get to 8. The goal for hydrogen is to get to 2. So let's start to sketch this out in terms of an electron dot or a Lewis dot structure. Okay, so we'll put our carbon in the middle, and then we'll put the hydrogen surrounding it. So let's start to talk about what happens. If we start with the hydrogen on the left, the hydrogen on the left says, okay, let me take my 1 valence electron and share it with carbon, and carbon in turn responds and says, okay, let me take 1 of my valence electrons and share it with you. And if they're going to share 2 electrons between each other, what type of bond are you going to form between them? You're going to form a single bond. And the nice part about that right now is that when the hydrogen does that, on the left does that, the hydrogen now has how many valence electrons? 2. So it's happy. Now we go to the hydrogen on the top. And the hydrogen on top says, okay, let me take my 1 valence electron and share it with the carbon. And the carbon says, you know what? I have another valence electron that hasn't been used yet to form a chemical bond. I'll share it back with you. And they end up sharing 2 valence electrons between them. And when the top hydrogen and the carbon share 2 valence electrons between them, what type of bond do you form between them? You form a single bond. And that hydrogen is now happy because how many valence electrons does that hydrogen have? That hydrogen now has 2. Well, it turns out that the hydrogen on the right and the hydrogen on the bottom want to share its 1 valence electron with carbon as well. And carbon has valence electrons that it hasn't used yet to share back, to form single bonds between them, resulting in the right hydrogen and the bottom hydrogen having 2 electrons total. But now, when all the pieces are filled in, what about the carbon? The carbon has 2, 4, 6, 8 valence electrons. and therefore its octet rule is satisfied. So for CH4 methane, this is how the carbon and the 4 hydrogens would come together to form a molecule or eventually enough for a compound. You'd have carbon forming single bonds with each one of the hydrogens. All right, so that's one example. Let's take a look at one more example. Let's take a look at NF3. All right, actually, let's change it up a little bit because we did fluorine already. Instead of doing NF3, let's just use another halogen. Let's do NCl3. So let's do NCl3. Okay. So what do we know? We know that nitrogen has 5 valence electrons. We know that each chlorine has 7 valence electrons. Well, the goal for everything here individually so the goal for the nitrogen and the goal for each of the chlorines, the goal for everything here is to get to 8. So let's start to sketch that out. Put our nitrogen in the middle. And then let's put a chlorine to the left. Chlorine to the bottom. And a chlorine to the right. Okay, so if we start with the chlorine on the left says, okay, let me take one of my valence electrons and share it with the nitrogen. And the nitrogen actually responds in kind and takes one of its valence electrons and shares it with the chlorine to form what type of bond between them? To form a single bond. And those 3 lone pairs of electrons on the chlorine, which chlorine on the left, which are not used in any chemical bond formation, they come along as well and stay on that chlorine, which works out perfectly because now that chlorine has 2, 4, 6, 8 valence electrons. All right. So the chlorine on the bottom says, okay, let me take one of my valence electrons and share it with the nitrogen. And again, the nitrogen has a valence electron that it hasn't used yet to form a chemical bond. So it responds in kind. Again, forming what type of bond between them? Forming a single bond. And those other pairs of electrons on the chlorine, those lone pairs, which are not involved in chemical bond formation, come along for the ride. And again, that works out well for the chlorine because the chlorine now has 2, 4, 6, 8 valence electrons. Well, the same thing occurs with the chlorine on the right and the nitrogen, resulting in a single bond between them. And again, that works out well for the chlorine because the chlorine ends up having 8 valence electrons. But then the last thing for the nitrogen is that the nitrogen has a pair, a lone pair, that's not used in chemical bond formation. So it comes along on the nitrogen as well. And when all is said and done, the nitrogen now has 2, 4, 6, 8 valence electrons. So now the nitrogen and each of the chlorines are happy because each of them have obtained 8 valence electrons, which is what the octet rule would want them to have.